Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today to introduce Daniel Wang. He has a PhD from Princeton University, working with Andrew Appel, who's a very well-known professor of computer science. Daniel worked on garbage collection while he was at Princeton, and actually his thesis was about trying to make the size of the code that you actually relied on without checking it as small as possible. And what he did was he took the garbage collector and tried to make that into a trusted component. He then went and worked in industry for a little while at a spin-off of Lucent called Gear. And he's now back at Princeton as a postdoc, and he's going to tell us about some experience he's had over the last few years. Daniel also interned as Microsoft Research, I guess in '98 it was, with Todd Probsting. So he knows all about Seattle. So welcome, Daniel, and it's all yours.
Hello. Being back here. I hope. So I had kind of a problem. I wasn't sure what level of technical detail. So if it's too much, tell me. If it's too little, ask questions, and I'm happy to answer them. So I want to start out with kind of a little motivation, so a little news thing. We saw this around February 4th, that Gosling's making wild criticisms about holes in .NET, and Don Box, of course, reporting that this is not an uncommon phenomenon in any large software system. And in particular, here is an interesting bug I ran across recently. So I just want to point out two things about this. This is 100% pure Java. There's no unsafe C code here. The only odd thing going on is we're using the reflection library, and actually particularly using this kind of very silly method in the reflection library that lets me violate the access declarations in thing. And we also have to be using the zip deflator library, which is actually implemented in native code. And because of those combinations of using the JNI interface to violate the privacy guarantees and the way the native code is linked to the system, I can cause it to crash the hotspot on Windows and also on Solaris and also on Mac OS. So this is kind of an example that bugs really occur, and it's really kind of a subtle interaction between the design of the reflection API and the native interface. The people writing the native code assume that when you declare a field private, it actually was, but the reflection API people say, well, that's not always a good thing, because sometimes we want to serialize the object and get access to private fields, but because of this combination, you can actually violate and crash the system. I've also verified that it crashes the JVM on Linux x86. And again, this is because it's an issue. The IBM people have licensed the Solaris libraries, so they licensed the same buggy code. And because it's part of the kind of core JNI libraries. And again, the issue is this: there's a C pointer that's being saved in the long field of a Java object, and it's called private, but the reflection API lets you bypass it. And that's kind of an example of the bug. So again, I ran across this bug when I was working with Gong Tan, Andrew Appel, and some others at NEC. We were trying to take Java native interface code written in C and apply George Nekula's C cured system, which is a way of taking unsafe C code and making it safe by inserting runtime checks. And we wanted to compare the performance of the cured C code with native Java code to kind of, so basically you have a choice of porting your unsafe C code to pure Java to get a fully safe system. But if you want a legacy solution that was fully safe, you could have also cure your C code with C cured and then link them together. And while we were doing that, the C cured system we developed pointed this weird pointer cast out. Gong said, oh, my system's too conservative because this should be okay because it's declared private in the Java object, but I have this thing against reflection because I know reflection had this feature to let you violate the privacy of this field. So I figured, oh, well, I can violate that with reflection and then kind of demonstrate the bug from there. So that's one little thing I've been working on recently. So I want to talk to you more about, so this is kind of the state of JVMs or virtual machines in general. How could we maybe potentially develop a fully verified virtual machine where there are no bugs of these sorts? We take care of all the interactions. So I dug up this reference someplace that basically developing the avionics code for the space shuttle is roughly $1,000 per line. So if you think about developing code of that quality, where you're putting up a $4 billion mechanical system with half a dozen people's lives, you would hope if you built a virtual machine at that level of quality, there'd be no bugs in it. And we did some analysis that if you look at the safety critical, is this working? The safety critical portion of a JVM system that's roughly 300,000 lines of code, and do the math, it's $300 million if you wanted to develop a fully safe virtual machine. So it seems very expensive to directly verify the system to do this. So one way of making this problem easier is this nice quote that's on Andrew Appel's webpage from Yuri Gurevich, who's at Microsoft. And basically, we can make this cost cheaper by using computers to check the proof that your system is somehow sound. This is not exactly easy to do, and you have to think about it. And doing this requires, as he says, a whole new discipline of which he's called pedantic. It's actually an interesting paper about constructive logic and proof theory, but it's like one little section in there that Andrew ran across. So kind of the goals of this talk is really to define my adventures in pedantics. I've done many pedantic things recently, and I'll tell you about them. And I really want to emphasize that the challenge, once you have a clear specification, verifying something is very boring, okay? The main difficulty is figuring out what you should verify, so you only verify boring bits that are really important, or do the boring verification on the important bits. I'm going to show two systems kind of in different ways how you can factor them so large parts can be verified automatically. And I kind of want to stimulate maybe a discussion about whether software verification is important or even practical. So I'll talk a little about my work in kind of briefly about type preserving garbage collection and mention some recent work in this area. As Manaver mentioned, I spent 2 years working at a Gear doing network processor design, so kind of hanging out with hardware people. And then I'll talk some more recent work about foundational proof carrying code and kind of the goals and where we are in this place. Okay, so this is how to get a PhD in collecting garbage. So just to remind us, so this is a certifying compilation approach. So the first big kind of insight was kind of made by George Nekula, that if you want to verify that native code has some property that's related to some source program, you don't necessarily have to type check or prove the correctness of the entire compiler. What you can do is you can have this potentially buggy compiler produce the native code plus a bit of evidence, which is either a typing derivation or a proof, and you can verify this independent of the correctness of the compiler. So if there's a bug in this compiler that produces evidence that doesn't correspond to the native code, and then your verifier will catch it up, and you go fix your bug in your compiler. But you don't have to verify your compiler to guarantee that any native code that runs has a particular property. So again, the big insight is you want to separate the witness verification from generation. The compiler is generating it. It may generate a buggy witness, but as long as you can guarantee the verification is correct, this is, my laser pointer is dying here, then everything's okay. So George Nekula gave this nice talk at Princeton, and then I kind of asked the question, but what about memory management? How do you deal with this? Because he was doing a very simple language with arrays, kind of Fortran style code. And this kind of led to the idea of a trusted garbage. So one way you can solve this is have a trusted garbage collector. So you could imagine a scheme where you have your native code and your garbage collector, which you verified by hand to have some property. But doing this is not exactly correct, because you really have to also trust the native code is respecting all the implicit GC invariants. So for example, you have to make sure if the native code is recording the proper live roots, they aren't using interior pointers or not XORing pointers, or lots of invariants the GC needs to have maintained by the native code to guarantee this correctly. So only recently, Carl Crary has defined a certifying compilation system where he can state what all the garbage collector invariants are for at least conservative collector, and he has a proof that if you had a trusted collector and your code checks, then you have some guarantee that things work properly. I kind of took a different tack.
So where has he published that?
In his foundational typed assembly, there's, I don't know if he's published, it was in that, it might be in a tech report, but I talked to him recently, and his notion of a valid state is appropriate for a conservative GC. So at certain points in the program, you're guaranteed that all the reachable data is actually reachable, or live. Say all the live data is reachable. So again, I took a tack similar to the issue of trying to avoid proving the correctness of the collector. What we want to do is basically emit some evidence with the garbage collector that we can verify. And in my particular system, the evidence is the type checking or typing rules for the garbage collector. And what guarantees can we get? We can get that if the garbage collector deallocates memory, so I'm not guaranteeing it actually does deallocate any memory, but if it does deallocate any memory, that memory is dead. And we also can get a guarantee that the garbage collector preserves the type structure of the value. So if it's an integer, it's an integer. If it's an object, it's an object. And before and after the execution of the collector, types are preserved. And since the collector is basically now verifiable, we can kind of verify this interface is correct, that basically the GC is calling the garbage collector with respect to its interface with the right set of alive roots and various things. So I don't want to go into too much detail, but the main trick is basically to treat the garbage collector as an ordinary program. Even if you do that, you have to kind of play some other games. To make the stack and root set explicit, you apply a CPS conversion with a defunctionalization. I don't want to bore people with compiler optimizations today. To guarantee that only dead memory is deallocated, we use a region type system, which is a type system developed by Toffman Taban and extended by various people, so you can reason about the safety of memory management. There's a little technical trickery required to deal with aliasing. Aliasing is always an evil thing, and my trick for region aliasing was to use a dynamic test. And the forwarding pointers, for those who are familiar with garbage collection, you typically have to leave a little hint about where the object got moved so you can avoid getting into an infinite loop when you're dealing with cyclic data structures. So I kind of coded together a very simple system and try to demonstrate you actually can make this practical. So the Popple paper has most of the details of what I've talked about. One number is a hazard, some basically charts. So basically you can ignore this, but basically the thing to take away is that I actually built something and it ran. I used the Milton compiler to run a couple of benchmarks using a type-preserving collector. Unfortunately, it ran a little slowly, mainly because I introduced some extra allocation with the CPS conversion to make some of the stack explicit. Then I finally finished the thesis, which includes some extended discussion about how to deal with some of the performance problems associated with the CPS conversion. And it's available as a CSTR, so if you want to download it and read it, you can feel free to. And there's a big proof at the end about various odd things about region memory management. So here's some recent work I did, basically with Matt Fluitt, who was at Cornell, who's now at Harvard, actually. So basically, Matt Fluitt was working with Greg Morrison on the Cyclone project, and they were talking about, coding up a scheme interpreter in Cyclone to demonstrate how useful Cyclone was. And we're curious about how, if you could write a complete scheme implementation along with the garbage collector in a safe dialect of C. So basically built and evaluated a type-safe garbage collector for a scheme interpreter by using Cyclone, which is a language with a lot of primitives for reasoning about memory in a safe way. So here's the Cyclone kind of sales pitch, but there's more information here. But the nice thing about Cyclone, it really has a lot of primitives for managing memory. It has a conservative garbage collector, it has a way of reasoning about reference counting in a safe way, regions, and a form of unique pointer or linear typing. It's rich enough to build a safe scheme interpreter. We just need one small little extra feature to build the garbage collector for the scheme interpreter, and this is basically dynamic region sequences, and I'm going to talk to you a little about those. So the idea of a dynamic region sequence, you can think about, so you have some region R prime, and then there's a next region associated with it, which we denote by the region next R prime, and then there's a next region after that. And with this invariant, you have this nice property that if the current region is some R prime, the place where where you're copying the data to is always in the next region. And this simplifies some difficulties I had in the original treatment of forwarding pointers. And kind of the invariant is as you move between to and from space, you can kind of transition. So you always have this invariant. To get this to work properly, we also have to add, we need a notion of unique pointer to enforce a particular allocation protocol. So we guarantees only exactly one next region alive at any point in the program. So here is kind of a scheme garbage collector written in Cyclone. Most of this is comments. I don't want to go into too much detail here. I've hidden all the really dirty work in this auxiliary function here, which is where the copy is. But this is the core allocation and deallocation loop. And if you want some more information, I suggest you look at the paper. So here's the comparison we do in the paper. We talk about 4 different systems. We talk about Cyclone, a Cyclone implementation of our scheme interpreter using our type-safe garbage collector. And this is the number of unsafe lines of code in its implementation, and there's 0 here. And the runtime system to run this implementation only requires about 1,800 lines of C code. It's basically kind of a fancy malloc library. And we also did a comparison with Cyclone using the same interpreter, but rather than using our handcrafted garbage collector, we relied on the standard conservative collector that came with Cyclone, which is basically the Baumweiser collector. And we also wanted to compare that against a fast, safe implementation in a language like Java. So Cisc is a schema implementation that runs on the JVM. It claims to be the fastest schema implementation out there on the JVM. I don't know if you believe that, but at least they make the claim. And this interpreter is written in Java, and so there's 0 lines of unsafe code in its implementation. Unfortunately, the runtime system is basically all the JVM, which is the JIT compiler and the garbage collector. So that's roughly, more than 200,000 lines of unsafe code to implement the runtime system. And then we wanted to compare against MZ Scheme, which is kind of a high-quality implementation of Scheme written completely in C. So the interpreter is unsafe. It's all written in C. The runtime system is also using the Baumweiser collector. So we just want to compare these 4 systems and see how they perform. Okay, so ignore the absolute. So the relative performance, this is the execution time benchmarks for a bunch of really small standard Lisp benchmarks. The numbers in parentheses are the execution time normalized to safe GC here. So if you look at these numbers here, you can see that we're pretty comparable to conservative garbage collector, the Baumweiser collector. When we compare to the Java version, we're doing badly in certain cases. Certain cases we're doing a bit better actually. And if you compare us to the completely unsafe version, we're doing really badly, except for this one point here. And this is because of the way it implements callcc. This is like a CPS version of the TAC benchmark using callcc, and they're using the stack, so they're copying a lot here. So what this tells you is that if you just compare the safe implementations of the scheme interpreter, we're roughly comparable. There's still a gap between completely unsafe system because they've pulled out all the stops in some sense. So there's a cost of safety. But if you are choosing between safe systems, you could say that this safe system here has a smaller TCB than the JVM version, which is comparable in performance. Okay, so here are some important lessons learned about collecting garbage. You really can build a garbage collector on simpler, easier to verify primitives. You don't need to verify the entire collector to have some guarantee about type preservation, at least. The main trick is you want to be able to type check everything, including the collector. It's not this magic piece of runtime system that's hidden in some library you never see. You should expose it to the type checker. Even without total correctness, we can get some interesting properties. Type safety is a very useful property. It's not a bad thing to have. And the real trick, or the real kind of exercise, is really figuring out how to factor the problem so we can just verify the important parts of the system, or the systems that are relatively easy to verify without having to verify the whole thing. Okay. So here's some questions you might be wondering. So we have a really fancy type system. And you might want to wonder, is that really fancy type system we have bug-free? So one question you might want to ask, are the rules we're using sound? Do they make sense with respect to semantics? And is the implementation of our type checker actually faithful to the rules? And maybe kind of another important question is, there's some corner case you can think about, and you wonder, can our type system deal with that corner case? There's professional performance trick you want to be able to do, and maybe your type system prevents you from doing that. And in fact, you can see that safety has some performance costs, mainly because we can't reason about all the important corner cases. This kind of leads to foundational proof carrying code and some of the work related here. And basically, I've been doing a lot of very boring proofs recently. To just review the certifying compilation pipeline, you have some program with some property. You run it through something you don't trust, and you verify at the very end. And then the natural question to ask is this verifier bug-free? So what does the verifier consist of? Well, it basically has to consist of a policy specification, machine semantics, so we have to understand what it means to execute something on the machine, some semantics for your type system, and then a very simple checker. Oops, this is just completely dying on me. Oops, I'll try this instead. You're both dead, okay. Yeah, I think it's flaky. The checker. And it turns out in the original PCC systems, there were a whole set of obvious lemmas about how certain things were true, obviously. And it turns out there are some bugs here very often. So the question of the foundational proof carrying code project is, how can we reduce this to the bare minimum? And basically, what do we mean by the bare minimum? Well, if you think about it, you can't really avoid this. You have to have a policy specification. You have to have a specification before you can verify anything. So you have to, the policy is part of the TCB. Machine semantics are part of the policy in some sense, and so are the type semantics and the checker. But these lemmas can actually be written in a form that can be machine checked, so we don't have to trust them anymore. So right now, these lemmas in the current Princeton PCC framework are around 100,000 lines of proof, and they're machine checked. So the current TCP size for the Princeton project work now is around 3,000 to 5,000 lines of code, depending on the specific policy you use. So if your policy is very expressive, then this gets bigger. If it's really simple, it gets smaller. So this is a project that started in 1999. It's quite old, actually. And I just kind of saw the beginnings of it as I was leaving Princeton and graduating. The project consists of certifying compiler for standard ML, where Jen Chen contributed to in the audience. A type checker expressed has a bunch of horn clauses about reasoning about what's valid typing, what's type safe or not. Machine semantics for the Spark, written in high order logic, and a machine check proof that the type rules used are correct. And the proof verifier, which is actually written in about under 1,000 lines of C code. So I'm going to really talk about some of the proof techniques we used in the rest of the talk. And this is here where people can feel free to tell me if I'm telling them too much or too little. So I'm going to talk about this slightly controversial issue of semantic techniques versus syntactic techniques, controversial in the POPL community at least. So the foundational proof carrying code project uses what we call semantic techniques as opposed to more traditional syntactic techniques. Unfortunately, the big proof we're working on has evolved over several iterations. And because of that, there are some artifacts in there that are a little confusing. So having spent some time trying to work on the real proof, I've also spent some time trying to extract from it a small little proof I could explain to someone. So the techniques we're using are pretty clear. And I'm going to kind of sketch or remind you of what the syntactic techniques are and also talk about semantic approaches and try to clarify some issues. And then I'm going to kind of summarize and talk a little about other PCC-related research. How am I on time? Or?
Yeah,
okay.
Half an hour in.
Okay.
Good.
I can take some time here then. So this is just the standard semantics for the untyped Lambda Calculus in a call by value framework. So I'm just curious, how many people in the audience can read this and be bored by it?
Yeah, I think you're going to lose.
Okay.
I have no idea what it's about.
Okay, so the Lambda Calculus, okay, so let's start with so this is the language of the Lambda Calculus. It's basically we have function bodies. This is a variable being bound in the body of a function. These are high order functions, or first class, right? This is the application of some expression to another expression, a variable or integer constants here. And the values, these are the things that programs evaluate to, are either functions or just integers.
What does it mean to bind a variable to an expression?
Sorry. Think of this as a function. This is a function whose input variable is called x. And x occurs in the body of E someplace, right?
Okay, so it's like E for an x, basically, if you were doing it. If this was code.
Yeah,
Yeah.
and see,
Okay.
this would be like there's a function.
body.
I see.
It just doesn't have a name.
Right.
Its form
Not in the
parameter
function.
is x.
Got it.
And its body is e, and you'll see x.
So this is basically defining by induction a relation, a step relation, that tells you when one expression steps to another. So this is the case where we have a function applied to a value, and we're going to step to the body of the function. This is a notation for substitution. So we're going to take every occurrence of x in E1 and replace it with v. So when I'm applying a value to a function, we just do this rule atomically. So if I have, there's a slight bug in these rules, but OK, this is fine. This should be v. I just realized that. But if I have an expression that looks like this, where this is a value, and this is some other expression, E2, I can reduce it in one step to basically this argument is unchanged. This has been modified, and this has been modified in the following way. It takes a step. This basically says left to right evaluation. So evaluate the left component of the application all the way to a value, and then reduce this. And when this becomes a value, then this rule applies. And this is the other case where we just evaluate E1 first. So
Did I miss something, or have we already talked about how, this is end-to-end verification, right? So
It seems like there's things that, are we talking about something that you have to test and a way to test it, or are we not?
I'm just giving you a
Here.
semantics for the machine. So here's a language. It has some meaning. It has semantics to it. And the next thing I'm going to talk about what it means to be, what property we're going to verify about it. Okay. So you'll notice if you look at this relation is partial. So for example, if you try to reduce an integer applied to an integer, you'd get stuck. There'd be no rule that would apply, because the only rule, these always have to be functions in that location. Okay. So this is a single step relation. It tells you when one expression takes one step, and we can define from this a multi-step relation saying any expression steps to itself in 0 steps, and an expression steps to e double prime in n plus 1 steps if it takes one small step, and then that resulting expression steps for n more. So basically we can talk about an expression taking n steps to another expression. And we can define a notion of a term being safe if for any n, if e reduces to e prime, then e prime can take a step or is a value. That means if I have an expression and I can do any number of reductions to it, that final expression is either a value or it can make progress. So for example, this expression is safe because basically you're applying 0 to the identity function here. It reduces to the value 0. This expression, I don't know if this is kind of if you're familiar with the Lambda Calculus, this is the kind of standard looping Lambda expression. So if you apply this substitution rule to this expression, you get it back again. So this kind of reduces to itself. Sorry?
E prime takes a step. What is the definition of E prime takes a step?
This one right here, that relation there.
I
Sorry.
read the definition. The term E is safe if then E prime takes a step or is a value. What does it mean, takes a step?
This takes a step means there exists some, basically this E prime is, there exists some other E double prime that's in this relation here, the single step relation.
Why paradoxical combinator does not take a step?
No, it does. It is safe. This is safe because it loops forever.
Okay.
So for any reduction, there's always one more step you can take. So it's safe because it loops forever.
So
This is clearly not safe because there's no step it can take.
Oh.
So every non-terminating expression is safe because it always takes a step.
So
This is safe because it's
safe because there's not a value, right? 0, 0.
Right, this is a value. This is safe because it loops forever. And this is not safe. Okay. Oops, now it's this.
And values are just natural numbers, right?
Natural numbers and functions. So the identity function is a value in some sense. So we have first class functions here. Okay. Okay. So for traditional type system, so this is a claim which you should.
The standard and restricted lambda calculus or something else.
Sorry?
What you described is a
Yes. Standard call by value in Lambda Calculus with natural numbers. So given this definition of safety here, with a little thinking, you can convince yourself it's undecidable because it evolves to termination, basically. You can reduce it to a termination problem. So safety in general is undecidable. But to establish safety in a kind of automatic way or using type systems, we can introduce a conservative approximation, basically a type system. And it's conservative in the sense that if the system says it's it's conservative in the sense that if you have an unsafe term, it will not be mistaken for a safe term, but it'll reject certain terms which are safe but not necessarily type safe. Okay.
Sorry, may I just motivational question.
Okay.
What is bad about these non-safe things that we declare them non-safe?
Okay.
I would expect to say something which looks to be non-safe.
So this is an example of a...
It is not a formal question, it's motivation.
Okay, right.
It's very unusual.
So most type systems are specified. First, you define a relation of this form. And you notice this relation is a partial relation. In particular, this is not allowed. This is a type error in the semantics because semantics get stuck. So if we know a program is not stuck, then we know there are no type errors in it. But there's a certain class of errors that don't occur.
It is not safe.
This is not safe.
Because I am asking French.
Okay.
I understand formal definition.
Okay.
Why do so? What is bad that it is not safe?
Oh, you might
Say
choose a
that
type
it
error.
doesn't present a type, right?
Right, right. It doesn't make sense to apply 0 to a non-function. So you encode type errors as making your reduction relation. Basically, if there's some property you want to enforce, you encode it. You make sure your step relation gets stuck when that property is violated. And then you develop a type system that guarantees it never gets stuck, and therefore you have a guarantee of some property.
So like, for instance, suppose you want to enforce in a program that you never write to a closed file. Okay, then you could imagine encoding that in such a way that if you ever try to write to a closed file, you'd get
Stuck.
a term that's
Yeah.
stuck. And so mathematically, what you'd be trying to do is find in your program whether you could get stuck like this, and that would mean you're writing to a closed file, which is the real thing you want to check. So.
Right. Okay. I just want to reiterate. So I'm going to kind of explain to you traditional approaches to type soundness. This is kind of standard textbook, well, not exactly textbook, but close to textbook. So this is a traditional type system for the simply typed Lambda Calculus, or one of them you can invent for it. So we introduce a new concept of a typing environment. So we keep track of the types of variables, free variables. So for example, n has type natural for any context. A variable has some type tau depending on what its type is in the context. Oh, sorry, that's a typo too. Never know. These are the slides I never look at because they're all the ones that are always boring. This should
You're
be.
going to have to explain
Yeah.
return styles too. So.
Okay, so you should read this as assuming the bindings of variables to types in gamma, you can show that n is, some expression has some type. So for example, if I have an application of E1 to E2, if I know under the same set of assumptions that E1 has an arrow type as a function from T1 to T2, and E2 has type T1, which is the right type for this expectation, then when I apply E2 to E1, I'll result in an expression of type T2, right? And this is the rule for type checking the body of a function. So here you assume that x. So if you want to show that this function has type T1 arrow T2, you assume in your environment that x has type tau, which should be tau 1. Oh, I hate this. There should be tau 1. And try to type check the body of E1 under that assumption. This should be a tau 1 here. I'm sorry about that.
What is an AT? It is just one type, or it is just...
It's one particular type, the type of naturals.
So everything is built from one type, by definition, right?
So, yeah, so this is, the types are either naturals or functions on naturals, or functions on naturals. Right, so. Okay. So once you have all this definition of the relations, you prove a standard type safety theorem. And a type safety theorem is basically if E is well typed under no assumptions, and for any type tau, then E is safe. That means it always makes progress. or is a value, or reduces to a value. You do this by induction of the structure of the multi-step relation with progress and preservation lemmas. The progress lemma basically says for any well-typed expression, it either takes a step or it's a value, okay? And you do prove this by induction on the the definition of the relation. And preservation says if E takes a single step to E prime, and E happened to be well-typed at type tau originally, then E prime is also well-typed at tau. So basically, as you reduce an expression, the type of the expression doesn't change, and any well-typed expression always can make progress or is a value. And with these two lemmas and this, you can prove the type safety theorem. Okay. So for example, the type system I showed you would accept this program right here, that 0 applied to any function is well-formed. It rejects this because there are no typing rules that apply to it, and this happens to be unsafe, which is a good thing. Unfortunately, this particular system is insufficiently powerful enough to type check this term. So even though we know this is a safe term because it's non-terminating, the type system I showed you can't type this term. In fact, actually, the type system I showed you here is only able to type check terms that always terminate. So these are only the strongly normalizing type safe terms in some sense. And the real problem with the kind of syntactic approaches, because they've been successful otherwise, is that adding kind of a special case to handle this term has a global consequence in the structure of the traditional proof. We have to, if you look at here, we're kind of providing, doing induction over the structure of the definition. And when we extend this relation to add an extra case, we have to kind of reconsider our proof. And it's just kind of a proof maintenance nightmare. So the FPC semantic approach is really trying to get the same guarantees of safety, but we're going to factor the problem in a different way, and we're going to try to improve the modularity of the proof. Sure.
Can you go one step back?
Okay.
So it is safe if it is in one step, it takes a step or its value.
Right.
Does it mean that something which is 2 steps back from an unsafe term is safe?
Oh, sorry. Okay.
I need progress rule.
So type safety is a stronger property than, right.
I mean that if I need for something like to take like 5 steps to reduction step to arrive to an unsafe term like 0, 0, it is still safe by your definition, right?
You're actually alluding to what I'm going to show you next, but
I just want to question.
so there are 2 issues. There's type safety and safety. Okay. So you can say that a term may be safe for 5 steps because for 5 steps it doesn't get stuck.
In your definition,
Right.
In your definition of safety,
Okay.
I just realized that in the definition of safety. So it is unsafe, it is like 0, 0, not a type, right?
Right.
But if after I apply one reduction step, I arrive to 0, 0, it is still safe, right? Because it is...
Oh, no. So the definition of safe here is, so if you have some expression and if for some number of reductions, so basically any possible reduction, so yeah, pick your, so basically think of the chain of possible reductions, pick any reduction, and at that point can always make progress. So basically it's saying the chain is infinite or a value. Okay. Okay, so here it might get even more technical. But you really...
Bad, I just don't get it. Why it is bad? I would say that people will say it is good if you reject paradoxical terms.
But, so this is okay, if you're a logician, you're very happy. If you're a programmer and want to write a program that actually doesn't terminate for whatever reason, or loops, or is recursive, you have a problem.
This program will loop, right?
Right.
Okay.
So,
It is safe.
yes. So this is just an illustration of how type systems are always conservative in some way. In a very simple system, it's conservative and kind of annoying. You'll discover if you develop type systems that every year is a new one. And there's a new one because the old ones rejected something that someone cared about. So you're always constantly extending the type system to incorporate more and more realistic cases. So here is kind of the distillation of the FPCC project, hopefully in one slide. Almost. I'm cheating. Here's a different definition of typing relation. So we're going to say, for example, naturals have type nat. And we're going to say some expression E has type tau if E happens to take a step to some E prime, and E prime happens to have type tau. And the typing rule here for functions is a little complicated, but if you think about what it means, it says, let's say I have some function with some parameter x, and I claim it has type tau 1 arrow tau 2. That should be the case if, give me any value of type tau 1. And if I replace x for that arbitrary value in E, if that resulting substituted expression where every occurrence of x is replaced with v has type tau 2. And if you assume this and if you can show this is true, then you can show that the function is in the typing relation. So another way of thinking about it is a canonical value, basically a value with a certain structure. So a type-safe expression, if you have a canonical value, that means it's a value of a certain structure. Or you have an expression that reduces to another type-safe expression, then that expression is type-safe. So there's one problem. Go ahead.
Sorry, yeah, I was going to say, but you're missing the induction step. Right?
Yes. There's no induction principle here that makes this relation well-defined. And this is the magic trick, the index model. So this was work by Andrew Appel and David McAllister to deal with an issue of recursive types. But the general technique they talk about is applicable to any kind of strange recursive definition. So you can generalize the index model. And in fact, actually, the index model is used, the indexes are used in 2 places in our current proof to save our, save our bacon in making things work. And I realized that, oh, wow, this is actually the real thing that makes everything work. It's the index model. So here is kind of the indexed approach. So rather than talking about type-safe, we talk about type-safe to a given approximation. So for example, n is type-safe for an arbitrary approximation, meaning that for, you can think about it, it's type-safe for I reductions or I observations. So you can put this in the context and you can reduce it for arbitrary number, and then we'll notice distinguish them here. So here's the induction principle. We say an expression E is type-safe for I plus 1 steps if E takes a step to E prime, and E prime is type-safe for I steps. And now we have a well-defined induction principle here. And for the function definition here, this is at I plus 1, and we're taking the approximation here at I. And if you think about what's going on here, to apply the function, you have to consume a step. So this works out nicely. So
now I see why you made that response to
Right.
Grigory's question, because Grigory was getting at like how far you are from something bad. Right? That is what you're.
So basically, we can talk about you're this far away from something bad, and if you can even prove that you're arbitrarily far away from something bad. Right. So this is the key insight in the foundational proof-carrying code SNM. So this is actually, so if you're familiar with semantics, people have tried to address these problems with domain theory and everything, but this kind of fell out as a very simple way of doing it, and is kind of a, when you write a proof on a paper and pencil proof, you have all these wonderful theorems that other people have developed for you, and you don't really care how complicated they are, you just use them. When you're formalizing everything from scratch, you're really looking for the simplest solution because you can't cheat. Everything has to be coded up. So I think some of the insight from the Foundation Proof Carrying Code project is kind of applying semantics in a practical way and discovering that, oh, there are like proofs on paper and pencil that are very hard to translate into mechanical systems. So you kind of spend some time thinking about how to make it easy.
Is it sort of related with logical relations?
Yeah, it's a general. So the logical relation, you're using type structure as your induction principle. Here we're using something a little, the step. So I took a slide out, but since you mentioned it. So traditional semantic techniques are using the type structure as the induction principle. This slide was motivated because when you start talking about recursive types, your type structure is now infinite. So you can't really use that as an induction principle. And if you read Mads Toft's thesis on polymorphic references, polymorphism and immutable references, he makes this comment that there's not a really good induction principle when you have heaps and stores and everything. And that's because the type structure really isn't the right structure to induct on. And the step relation has been very robust. We've been able to use that to, so basically the indexes were introduced to deal with recursive types. When we did immutable references, it turned out, oh, there was one place in the immutable reference proof where we need an induction principle, and the step induction actually works also. And if we're inducting in the structure, go ahead.
So I would say as a data flow and abstract interpretation person, I would say that's what we do. That's how you prove abstract interpretations as sound, right? You take the step and you do induction on the step and you prove that the fixed point holds or whatever. Right? Take one semantic step.
Right. But the semantics aren't really formalized to operational semantics, so that's kind of most of the. Anyways, maybe we should talk offline. Oops, wrong button here. Get back out of here. Okay. So what am I going to talk about here? Okay. So now, given this definition here, that's now well defined because of the index, I can prove this type safety theorem in a very direct way, because basically the definition to relation almost says if you're type safe for arbitrary I, then you're safe because you always can take a step. Basically, almost by definition. This is where the easy bit comes in. The real work is to prove these lemmas, where we define a new notion of being type safe with respect to some environment for an arbitrary number of steps. So you should read this as, here's some assumptions about the types of your variables. Sigma is a substitution that takes every variable to some arbitrary value. And we can say that substitution is well. This basically says every variable in the substitution is well typed or well formed to some approximation I, and this is the resulting expression with all the substitutions applied. And you basically can prove these inference rules, which are basically one-to-one to the original inference rules from these definitions. So here's a very technical detail. Okay, so actually the other thing we can prove by induction that this term has it has any type or arbitrary number of steps, which is kind of a natural thing to expect, that a non-terminating term can be assigned any type for any number of steps. So the one thing we lose in the semantic approach, so if you're familiar with syntactic approach, you typically have an inversion principle, where you know that, well, if E1 and E2 are well typed at tau 2, then it must be the case that E1 had some function type. We lose these principles in the semantics, because we're not computing the least solution to a bed of equations. We just have some model that's consistent with the typing rules, but it may not be the least model, so therefore we can't invert the rules. But this is not really a problem because we don't need them anymore in some sense. These are critical in proving progress and preservation in the syntactic framework, but we have safety another way. Okay, so here's the real proof formalized in higher order logic encoded in LF. I just want to show it to you to kind of give you a flavor of what it looks like. Or this is the end of the real proof. It's actually the final. So for example, here's what I can show to you that this program, PRG, is safe, where the program is actually an interesting program here. It's so the identity function is just the identity function here. This is the identity function applied to 0. So that's 0 applied to the identity function. Omega here is our non-terminating term. And here is the program we're going to show is safe. It's the identity function applied to 0. I'm getting some feedback here. Applied to omega applied to an unsafe term. So this term right here would not be type checkable in the simply traditional approach because it's not well typed at every subterm. But you can kind of argue that I don't really care about this. This is a non-terminating term. I'm never going to get that reduction, so this is safe. So here's the typing. This is a proof that the identity function is well typed. This is a proof that the identity function applied to 0 is well typed. And this is a proof that this program here is well typed. And it's composed by using this rule for combining the derivations for the application. Basically, you're applying two terms. So I can show this subterm is well typed. I can show that subterm is well typed. I'm happy. I show this subterm is well typed by using this typing rule, which basically I'll show you later. It says that if a program is provably divergent, then it's type safe. And then from here, I can just convert the proof of type safety into safety with this judgment. This is kind of a flavor of what the actual, nitty-gritty looks like. So here's actually this particular ad hoc rule with a proof. So we're going to find a notion of divergence. Something diverges if for any n, this is our multi-step relation. If it takes a step for an arbitrary n e prime, then for any n, there's another step it can take. basically what it means to diverge. This is the important thing to know, that just as a user of the rule, you can just read it this way. If I can prove E diverges, then it has a type for arbitrary n and t, and you really don't need to know about what's going on there because it's machine check. And it's kind of, these are actually much easier to write than read. Here's a problem for maintenance, actually. It's much easier to write the really unintelligible proof. It's much more pain to maintain that proof. Anyways, so I don't know if, okay, this is even a more technical thing, but kind of my motivation for this is the current proof system we're using right now in Princeton is using first-order encodings of binding. So it's using the Brownian indices in explicit environments. And if you ever program these in a compiler, they're a real pain to get right. And I was responsible for writing some rules about substitution in the Brownian indices and proving them correct. And it was really, really boring. And I knew about higher-order abstract syntax, which is this approach that's been used in a lot of theorem proving communities. And I wanted to use that. And I asked Andrew, so why didn't you use high-order abstract syntax? And his answer was, I wasn't sure it would work. And I thought about it, and I think it should work. So I've been spending some time trying to build a demo of this. So I'm trying to build a complete end-to-end demo of this for that very simple calculus I've showed you right now. And again, if you really want to know, I have proofs to show you. Okay, so I just kind of summarize the advantage of the semantic approach. I think the real thing is that adding ad hoc rules to your system is easy. It's not this carefully crafted relation that, if you add an extra rule, it's going to destroy all your properties. It's kind of this general framework. Really, the standard syntax techniques are not as modular. And with semantic approach, I think you can build verification systems in a modular way, because the program semantics is the truth. There's nothing to argue about. The program behaves a certain way, and you can either prove a property about it or not. The syntactic approach is a little artificial in some sense. But of course, there are lots of other valid competing approaches, and I just want to kind of give you a short FTC bibliography. So the most recent work was this open verifier that George Nekiel has been working on. It was at TLDI recently. And he's generalizing his original proof-carrying code project into a more foundational flavor. Before that, there was a paper by Carl Query, which I mentioned a little earlier. And he uses a traditional syntactic technique to prove type safety with a different logical framework. Yet again, there was another traditional syntactic approach to foundational proof-carrying code using yet another logical framework in yet another system. And then finally, this is the kind of the earliest survey paper about foundational proof-carrying code that Andrew had written. Even though the project started in '99 with some earlier papers, but this is a good survey of everything. So kind of lessons learned. So foundational verification of important properties. These were actually verified at the level of the machine code. It's actually easy. I mean, it's been done by a bunch of academics, so it must be easy, right? There really are at least 4 independent approaches that all work. I think they all work at different points in the design space. Most of the kind of fights we're having, these are engineering questions about how the proof should look. There really aren't any fundamental problems to this. There are a lot of engineering challenges, and there are a few, I think there are maybe a few semantic questions that are open, but I think we can do it. And I make this kind of claim that for several $1 million, not 300 million, but several million, you can build a verified VM, and that's kind of the things to think about. So I just want to close with some thoughts. I think they're clear that there are many useful tools out there for verification of software. And the real challenge today, I think, is to improve the tools. Improving the tools is an important thing to do, but we also have to kind of learn to apply the methodology in the right part of the system. Because I think this is something maybe a little controversial to say, but I think right now the way tools are used are to kind of make products better by getting rid of the bugs. But if you really think about it, you could use verification to kind of open up new businesses and markets. If I can make or you can use it as a marketing strategy. I have warranted software. I have software that's guaranteed to be bug-free for a certain class of bugs. Your competitors don't. And as the customer, do you buy the code with a warranty or not? So that's a way of differentiating your product in a very significant way.
How do you warranty? Will you pay to someone?
I go to Lloyd's of London and I say, look, it's the following formal verification framework, this following process of software development, and we're guaranteeing against this class of bugs, for example, buffer overruns, that the kernel is buffer overrun free. And you talk to the insurance companies, and they say, okay, if you're going to insure you against this, you pay this much, and we'll guarantee that much, right? So I mean, it can be done. I mean, Lloyd's of London will insure anything, right? And it's a question of the cost of insurance, and that.
Personally willing to pay for a significant amount to people.
Sorry?
Are personally willing to pay significant money to those who will find bugs in the program that you guarantee to have no bugs.
Right, right. So, yeah. That's one way of doing kind of a bug bounty approach. Or, again, if you have a proof that something's true, then you can warranty it however you want. I mean, it's a proof.
There are a lot of mistakes found in the proof like 10 years after those proofs were published, right?
Right. So the issue here is that these proofs that I'm talking about are the ones I've showed you are machine checkable. Right? These aren't paper and pencil proofs.
But you can make mistakes running those programs for machines which check your proof, right?
Yes. So there's a whole issue of assurance. So the way our system is structured right now, the minimal verifier is 1,000 lines of C code.
So you're making some probabilistic statement when you're saying that you make guarantee, right?
Yes.
Because otherwise you wouldn't need to involve insurance companies.
Right.
Yeah.
All statements of truth are all statements of truth are level of assurance. The way I say is how much you're willing to bet. You know, some things you bet over lunch, sometimes you'll bet your life on. It's the case that people build safety critical software, which is much bigger than people are willing to bet their lives on. So we should be able to bet a few $1 million on on some claims. But anyways, so that's all I really had to say. If you have any more questions, I'm sure we'll talk about them. Or...
I have a question.
Sure.
So is it possible to apply these kind of tight proofs to encryption algorithms and to somehow prove that an encryption algorithm may be difficult to break?
Okay, so there are two issues. So encryption algorithms, that's P equals NP. So the answer is no. But there are work who are analyzing encryption protocols. So I have some encryption protocols that can be very complicated, some key exchange protocols. And if you make some assumptions about how the cryptography works, there are formal verification frameworks. You can verify your protocol, like there's no attacker that can inject a message that caused your protocol to misauthenticate you. And I think there was some work by Benjamin Pierce, who was saying, let's say you program, you want to guarantee some abstraction property that your program can't look at this data. Okay, and you can prove this formally, assuming some type system. And he has some way of taking that type-based argument and turning it into a cryptography-based argument, saying as long as you keep this code encrypted during this part of the program, then the program's behavior is independent of the actual data underneath it. So there's some ways of, so cryptography, it's the question about other one-way functions versus P equal to NP, we don't know. But there are definitely some ways of using formal techniques to leverage the protocol process, which can be very error-prone also. Any more questions? Okay. Oh, thank you very much.
Thank you, Dan.